Okay, the last part of the lesson we're going to be looking at looks at domain and range. And so here's some more terminology. The domain looks at the set of all first elements or x values in the relation. Or in other words, it's all the possible x values that exist for the relation. The range looks at the set of all second elements or y values in the relation and all the possible y values that exist for the relation. So what we're going to be looking at are the different values of x and the different values of y that can exist for a particular either graph, function, or specific points. Okay, so the notation that we're going to be using for domain and range will be a set notation because you are looking at the set of all first elements or the set of all second elements. And so there's a specific set of brackets we use in order to look at a set, and the brackets look like brace brackets. Okay, and so if you don't know how to draw brace brackets, I'll show you now. To do the opening one, you draw an S, and then you can draw a 2. And to do the closing one, you do a 2, and then you draw an S. Okay, so in case you don't know how to draw brace brackets, there's a simple way to try to do it. Okay, back to domain and range. Domain and range, we did look at this last year, but we didn't call it domain and range. All we said is a set of possible y values and the possible x values. That's all we really used last year. Okay, so we're going to go straight into looking at some examples. And so for this example, it asks us to state the domain and range of each relation and then determine if each relation is a function. Now, depending on if you're given a specific set of points, which is what we're given in the first one, or if you're given a function, which means you'll have a wider array of points because all the little points in between still count. The notation that you use is slightly different. Okay, first of all, if you're given a set of points like you are here, then you're not told whether you're looking at x and y. You just know you have two coordinates. We don't know what the two coordinates are. It could be time and height for all we know. So we're not going to use any variables to represent our first element and our second element. Okay, so I'm going to use capital D to represent the domain, and I'm going to use an opening brace bracket to help me start this off. And so because I'm given a specific set of points, I know that the domain will only include all the first elements that I have here. Okay, so there's all the first element values. Now, typically when you're stating the domain, you want to write it in a numerical order from lowest to highest. So the lowest value I have for my first element is -4. The second value, the second smallest value I have is -2. And what you'll notice is that -2 actually repeats itself. You don't need to write it twice. Remember that you're just listing the different values of the first element that you can have. So you don't need to say it twice. You know that you can have -2. Okay, then we have 1 and then we have 3. Okay, so there's a set of all first element values that you can have. Okay, when you're given a specific set of points, then you just need to list them in numerical order from lowest to highest. Okay, so this is what happens when you're given specific points. Okay, and by specific points I also mean none of the values in between these points actually are included in this relation. And what I mean by that is, if I plot these points, I wouldn't connect them. They would just be like a scatter plot. There would just be a bunch of random points on a graph. Okay. Okay, in terms of the range, I'm going to look at the second element and see what values I have there. And so for the second element, you'll notice that the smallest value I have is -2. So the set of values include -2. And then the next value I have is 1. And again, 1 repeats itself. You don't need to list it twice. As long as you list it once, you're saying that it's included in that set of points. So -2, 1, and 3, and then 4. Okay, so there's your set of all second element values that you have. Okay, and again, this is the notation for domain and range when you're given specific points. Nothing in between these points are included. It's just those particular points. Okay. Now, the last part of the question asks us to state whether or not the relation is a function. So what are we looking for? We're trying to see if each x value has a unique y value. So ideally what you want to see is if there's any x value that repeats, and in this case we do have an x value that repeats, and we want to see if the y value is the same or if it's different. If it's the same, then it would be a function, but if it's different, then that means that that value of x has too many different values of y that correspond to it, and in this case you'll notice that it's not a function because x equals -2 has multiple values of y that correspond to it. So this one is not a function. Okay, now we're going to look at an example where you're given a relation. And based on this relation, we want to know whether or not this is, what the domain and range is, and whether or not this is a function. Okay, so let's take a look at what kind of relation we have here. We know it's quadratic because there's an exponent of 2. So it's harder to figure out what the domain and range is when you're just given a relation because you don't know what the specific set of points are, and there are an infinite number of points. Now, because there are an infinite number of points for this particular relation, that's why we write the domain and range in a different way. Okay, and so let's take a look at how to graph this. Sometimes sketching the graph of the relation will help you figure out the domain and range a little bit more easily. And so I'm going to start looking at the vertex here. And I know the vertex is at 3 and 1. The graph is shifted to the right 3 and up 1. We actually sketched this earlier. So we're just going to do it again just so that it's with the question. So we have the vertex at 3 and 1. The a value here tells me that the graph has been vertically stretched by a factor of 2. And so I could use a step pattern by going over 1 and up 2. And then going over 2 and up 8 instead of 4. Or you could just sketch it. It's not that big a deal because the points are not what we're looking for in this case. And the reason why we're not looking specifically at the points is because there's an infinite number of points in this graph already. Okay? So when you're given a relation, it's not just a set of points. It's a bunch of points that create this curve. Okay? So it's a bunch of different little points. So anything between x equals 3 and x equals 4 is still a bunch of little points that actually create this curve. Okay? So the notation when you write the domain and range, when you're given an array of points, so when you're given a bunch of different points, or when you're given a function or a relation, actually does change. Okay? So I'm going to start by writing d equals. And so the way you write the domain is, first you indicate what set of numbers it is an element of. Okay? And because my independent variable in this case is x, I'm going to start by writing x is an element of all real numbers. And what this means is x belongs to the set of numbers that are real numbers. Real numbers include positive and negative whole numbers, positive and negative decimal numbers. So all the decimal values in between, so at like x equals 3, 3.1, 3.2, 3.000000001, all the way up to 3.999999994 are all included as well. Okay, so that's what all real numbers represents. The real number system has positive and negative whole numbers and decimal numbers and fractions and all the values in between. Okay, and so I'll just write down what this says. This says x is an element of all real numbers. Okay, so now again, this is going to be a little bit different because you're looking at the domain of a wide array of numbers. And so what you're looking at is the set of values of x that you can actually have. So first of all, we've established that it's an element of all real numbers, since it includes all the decimal values and fractions and whole numbers in between. Now what we want to know is if there's any restrictions on this domain. What that means is our domain looks at our horizontal values. And if you actually look at this graph, it goes infinitely towards the left. So this will forever continue towards the left. And this will forever continue towards the right. Okay? You're looking to see if there's a left bound or a right bound on the actual graph. Okay? And in this case, because there is not any restriction, then we know that the domain contains all possible x values and from negative infinity all the way up to positive infinity. Okay, let's take a look at the range. The range is going to be a little bit more interesting here. Okay, so the range in this case looks at the set of all y values. And so what I'll start with is by writing y. And what you'll notice is that for the y values also, there's a bunch of different values in between that go towards positive infinity. And so what we're going to start by writing is y is an element of all real numbers. And then we're going to see whether or not there's a restriction on the y values. Now, the y values are the vertical values that we have here. And so we want to see if there's a lower limit and an upper limit. Okay? If there is either one of those limits, then that means that there is a restriction on the domain. Now, what I mean by restriction on the domain is that there's only specific values of y that you can actually have. And so let's take a look at the graph. First, we're going to see if there's a limit as to how high our y values can go. And you'll notice that because there are arrows at the top, this indicates that my y values continue infinitely going towards positive infinity. They can be any value of y all the way up to 150 and even higher, wherever you want it to go. Okay? In terms of a lower limit, so let's see if there's a limit to how low the y values can go. And what you'll notice is that the lowest y value I can have is 1. There's no way for this relation to have a y value that is lower than 1. It can't be equal to 0. It can't be equal to negative 1, negative 2. Can't be equal to negative a half, negative 2.5. None of those values actually exist for y. So in this case, what we do have is a restriction on how low y can go. Okay? And the restriction is that the only values of y that I can have are values of y that are greater than 1, so higher than 1, and that are equal to 1. Okay? So, how do you include that restriction in the range? You write y is an element of all real numbers, such that is just a vertical line, y is greater than or equal to 1. And that's how you would write the range. So you're going to state that it's an element of all real numbers and then state any restrictions, if there are any, right afterwards. Okay? So what this says is y is an element of all real numbers and then that vertical line says such that y is greater than or equal to 1. Okay, that's what that actually says. Y is an element of all real numbers such that y is greater than or equal to 1. Okay? Alright, so last part looks at whether or not this is a function, and so we can do the vertical line test since we have our graph. And so if we do the vertical line test, you'll notice that each x value has a unique y value. And so this is a function. Okay? And this is actually a quadratic function, and we'll talk more about that later.